Okay, so I think we can start. Good morning to everyone. Welcome to this first section this morning. And the first speaker is Giovanni Li Manni, that will talk about the latest result of his research. So please, the floor is yours. 15 plus 5.
Thank you very much. 5. No, I don't think that's so. Okay. So thanks for the kind introduction, and good morning, everyone, to the last day of this OpenMolcas development meeting. So I've seen some new faces. So I think it's fair to say that some people might not know me. So my name is Giovanni Li Manni. I'm group leader at the Electronic Structure Theory Department, Max Planck Institute for Solid State Research in Stuttgart. And these days we've been here together with Oscar Vesa, who is a senior PhD student in our group, and Arta Safari, who is the youngest PhD student joining our group. So in this slide, I summarize our latest contribution to the OpenMolcas project. Many of you might have crossed my papers about generalized active spaces that can be used to truncate wave function or build a specific type of correlation into your many body wave function, or for instance, what Francesco and his group is doing. If you want to do, you want to freeze the occupation number in a certain subspace and so on and so forth. This was already done in 2011 in collaboration with Laura Gagliardi. So the conventional GASSCF has been there for a long time. You might not know my contribution into the OpenMolcas project through the MCPDFT, the multi-configurational density functional theory, and the latest contribution comes from the Stochastic-GASSCF and Stochastic MCSCF procedure in general. The first implementation we interfaced within Molcas was in 2016 through my collaboration with Alia Lavi, the director of the Electronic Structure Theory Department. And back then we had only Slater determinant based expansion. So our CASSCF was based on Slater determinants. In 2021, mostly thanks to the work of Werner de Braus, was a PhD in our group. We had spin adapted Full-CI and thanks to that we reached the spin adaptation. So we have a stochastic spin adapted stochastic CASSCF. That form of stochastic CASSCF actually is very close to the CASSCF we normally historically have been using in Molcas, conventional deterministically, because we actually use the same many body wave function representation. In both cases, it's GUGA. So you will be familiar with the up and down and so on and so forth. Unfortunately, and in that respect, in this research, while working on this research topic, we realized that there was a spectacular symmetry into the many body wave function whenever whenever the Hilbert space is built using cumulatively spin coupled bases, such as the CSF we have in GUGA. And that leads to what we call the wave function compression. By simple molecular orbital transformation, you can have a very, very compact representation of the multi-configurational wave function. And that arises from a specific block diagonal structure that you observe in the entire Hilbert space. So this compression applies to ground state and excited states and simplifies a lot the life for methods that take advantage of the sparsity, such as FCIQMC or other methods like let's say, selected CI approaches. I hope to have the time to discuss this in more details. GUGA also comes with some limitations, especially when you go to large active space calculation. One of them is that it's not easy to evaluate higher order excitation operators, such as the one that are needed to get 3 and 4 body density matches, and therefore it's not easy to get CASSPT2 up and running out of the box. For this reason, and also the same applies if you want to do, for instance, just correlation that Pablo in our group was discussing a couple of days ago. So if you want to have dynamic correlation top of stochastic CASSCF in a spin adapted basis, that's not the straightforward way of doing it using GUGA. It is possible, we're working on it, but it's not immediate. So we had to look back, to do a step back and go to a Slater determinant basis. And there then the question arises, how can we be absolutely sure that we can control the spin? That is extremely relevant for my type of research or the research in your group when you're doing you're studying magnetic interaction in polynuclear transition metal clusters. So actually the answer, we found the answer. It was easy and it has been around in our community for a while, and it's based on a simple modified Hamiltonian where we have a first order spin penalty. And I think we got the paper recently, a couple of months ago, and I will be discussing about this during this talk. As I said, we had the GASSCF since 2011. Last year, we came up with the Stochastic-GASSCF. So that is an substantial advantage compared to the MRG. In the MRG, you can't create this subgroup partitioning wave function. Back then again, it was a Slater determinant, and we are very close to have the spin adapted implementation. Oscar is currently working on it. I think we have a pilot version, and we hope to have in a couple of months some substantial calculation where we have the spin adapted version of the Stochastic-GASSCF. Arta Safari joined us a few months ago, and he has been exploring state average in CASSCF. I think it's time to move on to excited states and dynamic correlation and so on and so forth. So I'm looking into that. I hope in a couple of years to have some advances in that direction. So we have now some sort of pilot analysis of what happens if you do state averaging stochastic CASSCF and across the spin and point group symmetry. So these properties has not been available in MolCas. And I think every year, every time we have an OpenMolcas meeting, people ask, are you going to have a state average across the spin? This is available in other codes. I think Orca does it, and some other code also do it. We don't have it there because it's kind of algorithmically tricky how to separate all the different blocks of the Hilbert space. It can be done, but it's kind of tedious algorithmically. But now with this sort of loose interface that we go through NISI, of course, it becomes trivial. So we are looking into it, and I'm sure that Arta will be very happy to share our preliminary result in that respect. So the talk is organized in, first I give you a feeling about advantages, disadvantage of using the GUGA versus Slater determinant basis. Many of you might already know. Then I dig a little bit into the details of the spin purification approach. And finally, if I have time, I will go into some elements of this fantastic wave function compression that we see in the many body wave functions. It's a topic that I've been discussing already last year, and maybe the two past meeting, but I think it's so beautiful and we keep learning about it that it is worth to kind of keep reminding, especially for the new people joining our community. So there are many advantages and disadvantages of the two different bases that are currently most used in in multi-configurational methodologies. I'm not going to go through all of them. In green are the advantages, in red are the disadvantages. And probably what people know the most is the first point, that the Hamiltonian matrix elements are very easy to evaluate in a Slater determinant basis because you can rely on the Slater Condon rules. That is actually not the case in the GUGA basis. There, the evaluation of Hamiltonian matrix elements is a little bit more involved, and also the Slater Condon rule kind of break down. So it's not granted which elements are coupled by single and double excitation. That create also a new problem, which is that the Hamiltonian matrix is generally more dense than its Slater determinant. That is also kind of annoying if you are doing a method that take advantage of sparsities. For instance, in Full-CI that would be a damaging factor. So Werner went through all these problems within the Full-CI and we managed to have a working machinery. But this working machinery became really, really powerful once we realized that there was this trick of doing simple molecular orbital transformation and compress the wave function. Suddenly a calculation that would last for weeks, then it became like a one minute optimization process. I want to focus over to disadvantages of coming from the Slater determinant basis. With Slater determinant, you can easily have access to spin projection properties. We have the spin resolved density matches for free. And very easy, you can have easy access to high order reduced density matrices, and you can immediately, out of the box, basically couple to perturbation theory in the form of CASSCF. You can also couple it with the transport related method that Pablo was introducing, so that one can be kind of come for free. And you can also immediately couple to the tailored coupled cluster, which is a formalism entirely based on Slater determinant basis. Additionally, you can also kind of play around with Hamiltonians. You can use modified anisotropic Hamiltonians that allow us to explore exotic form of magnetism in molecular systems. Therefore, it's obvious that we might want to have a later determinant-based approach, but at the same time, we want to retain the control over the spin. And as I said, that is crucial for my research. We do that, and we implemented within the Full-CI and therefore the stochastic framework using spin purification. I got inspired by a Li Manni paper from 2017, but as I said, this type of argument was already around. I think in the MRG, in the old DMRG implementation, they've been already using this approach. But in Li Manni paper, he advises they tested different approaches. Some of them are purification, first and second order purification approaches, or they use projection techniques or inverse iteration. Their conclusion, based on, I think, simple Davidson diagonalization type, was that the first order spin penalty was actually the optimal choice. Both algorithmically, it's very easy to implement, and computationally, it doesn't have a big overhead. So I went to look at it with the eyes of a Full-CI-QMC, from the eyes of from a Full-CI-QMC perspective, and indeed it turned out that it's extremely simple to have it implemented into Full-CI-QMC. All you have to do is to be, instead of the bare Hamiltonian, to have this modified Hamiltonian that is simply corrected by the JS² operator. J is a number that the user must choose, and it shouldn't jeopardize us. Oscar will go in a little bit into the details, but unfortunately we introduce a parameter that need to be tuned in a way to make the low spin state in the modified Hamiltonian the ground state of the electronic spectrum. And then we have the S². Now this term will of course shift the eigenvalues proportionally to the value J times SS plus 1. And so the higher spin multiplicity would be shifted proportionally higher compared to low spin states, fixing the J parameter. So if by that choice of J, you are able to create a sort of antiferromagnetic ladder in the modified Hamiltonian, then you can easily target specifically the spin state that you are interested in. And you can go higher into this spin ladder by playing with the spin projection. So you control the spin by the MS value of your later determinant function. Now the eigenvectors, of course, they are the same because H and S² commute. So that is the good news, and the energy from the energy of the bare Hamiltonian can be retrieved by, for instance, in our case, you can calculate the projected energy only for the energy evaluation. You do the projected energy of the original Hamiltonian, while the simulation, the dynamic, is carried in the modified Hamiltonian. Or you can do it a posteriori. You can calculate the energy as expectation values coming from the reduced density matrices, of course, contracted with the original Hamiltonian. In terms of computational cost or algorithmic involvement of this modification, just to stress how simple it is, I showed here the S² matrix. The S² matrix is extremely sparse, and in particular, we see that the diagonal terms have an SZ times SZ minus 1 term that is constant if you're working as later determinant with a fixed MS value. And then you have this n open shell alpha term. So in other words, whenever you are looking at the class of later determinant where all the electrons where all the electrons are paired up, you will have n open shell alpha equals 0. Then if you have one pair that is unpaired of alpha and beta, you will have n open shell alpha equal 1, equal 2, and so on and so forth. And in this matrix, you simply see these kind of large blocks that are diagonally shifted by these diagonal terms. And then you have the off-diagonal. The off-diagonal are non-vanishing only whenever you have exchange interaction. So if they are spin flipped from each other, then they will have this contribution here, where the sign, as always in second quantization, is given by the product of fermionic phase factor, and which I guess we are used to. And any term that is not the spin flip, then it wouldn't be coupled. So that is where the sparsity actually arises. So in other words, and this actually this rule actually is what identified as small blocks, because these small blocks are the ones that share the same all those later determinants that share the same occupation number vector, is the same distribution of electrons into the orbitals, and they only differ by spin flips. the number of terms you have on each row is equal to n over shell alpha times n over shell beta, which is the combinatorial sort of number of pairs of alpha and beta you can pick and you can flip in order to have a non-vanishing term. And so by this sort of structure, you immediately realize that this matrix is extremely sparse. And once you go again into Full-CI QMC, you have this very, very, I would say, simple implementation that whenever you are exciting from a determinant to another determinant that is an exchange, then you can add this correction multiplied by J. And if you are in a diagonal term, so in the depth step, then you will be adding this term here. And both of them are extremely cheap to calculate. So the computational overhead is basically negligible. Now, Oscar will be going in a little bit more in details, but I want to simply show in practice how this works. This one would be the dynamic for that system there, and that show high spin ground state. If you have a later determinant based Full-CI QMC, this is the dynamic that you see it's converging gradually to the high spin energy when J is equal to 0. And you can keep a J, let's say the green one, J equals 0.02, where instead the wave function it gets trapped into the low spin states. And you can monitor these things into the spin expectation value, for instance. You see that for J0, small j, the spin is actually not compatible with the doublet, which would be this state here. But when your J is big enough, you actually are bang on the pure spin solution. So there are some conclusions to draw. It is possible to have spin purification. It is cheap, easy to implement, and the most important, give us access to things that normally we wouldn't be able to do right away, such as CASSCF or the transcorrelation. Of course, as I said, there are some limitations. One of them is the practical annoying step that you need to play with the J. You need to choose a J that makes your modified Hamiltonian ferromagnetically ordered. And the other problem is that, of course, you cannot enjoy all the compression that I will be talking shortly in the next slides. So in that case, then you have to deal with a dense sort of Hamiltonian, and that will slow down the Full-CI QMC procedure. Or if you are in selected CI, that will be also sort of the limiting step. Compression, yeah.
So do you ensure to initial guess at least has the right spin symmetry? Because typically this purification scheme, you always also try to start from the right place, so you don't have to slowly converge to it, but you start in the right place and you just stay there.
Okay, so our dynamics, yes, you can do that, of course, but that means you need to have absolute knowledge of all the Krebs-Gordon coefficients that the couple that's later determined in a way to have a good starting point. That is obviously, if you have a 1550 active space, that's kind of already hard per se to do. And plus in NISI, you always start from a single reference determinant. So you go to choose just a determinant that suits the MS, and then you keep on moving from there. Okay, so compression of the wave function. We observe that within the GUGA formalism, it is possible to compress enormously wave function, ground state or excited state, and rely on simple chemically motivated molecular orbital transformation. You actually need three ingredients. One is you need to have a chemically motivated transformation, so you need to know a little bit of the physics you are kind of chasing or you are looking after. You need to have a cumulatively spin coupled basis like we do in CSF used in GUGA. And the third ingredient that is useful, but not, of course, not necessary, is that you might want to have a graphical representation of your configurational space. And that normally we learn as a students using the genealogical branching diagram. With these three ingredients, you can actually navigate the Hilbert space in a spin-adapted basis. And that is extremely advantageous for methods that take advantage of the sparsity, such as Full-CI QMC. That's the playground we learn from. But I'm pretty sure if you have a good implementation of selected CI, they will be able to do the same sort of compression approach. This is a practical case. I took, again, the same system. This is a Cas99, and I was trying to target the doublet spin state. If you take the natural orbitals and you build your CI wave function for the doublet ground state, you would have more than 1,000 non-negligible and nearly equally weighted CSF. So you will not be able to understand what is the physics of this wave function. You can localize the orbitals, and you would have 42 non-negligible terms. Still, you are not able to grasp the physics underneath this wave function. This 42 is not an arbitrary number. It can actually be found in the genealogical branching diagram. If you build 9 electrons coupled to doublet, actually you see that you have exactly 42 spin coupling. These are the terms that show up in your wave function when you solve the GUGA eigenvalue problem. You can cyclically order them, which means you take first all the orbitals of site 1, then the orbital of site 2, and then finally the orbital of site 3, and you see that actually you end up with 9 non-vanishing CSF. This 9 is again given by a genealogical branching diagram that can be navigated, and that's the number. It's more embarrassing when you look, for instance, at the quartet spin state, because this one literally becomes a single configurational wave function in a GUGA language. Yes, I close. That is what is behind this compression. You have a very dense Hamiltonian, and this is what happens when you do this molecular orbital transformation in exchange couple sort of ionic magnetic systems. You have this block diagonal structure, and by the trial wave function that you can monitor through the genealogical branching diagram, you can choose from the genealogical branching diagram, you can select something, the trial wave function in this block, and you will be trapped into the lowest state of this block. So this one is not only a way to get a selective optimization of excited state without dragging the entire optimization of the lower energy spectra, but also it allows you to, for instance, diagonalize the different blocks. Yes, I close. I want to just make the point for the DMRG people, this is not what we do in the MRG. This is completely different. I have the proof, we can discuss, unfortunately I can't. So, and the last cool feature is that we can go bigger. For instance, last year I was already playing with this FIMOCO model system. You can implement a genetic algorithm for exploring the permutational space because you need to have a sorting of the orbitals. And yes, you can reach compression even for FIMOCO. With that, I skip that, and I thank my collaborators in Stuttgart and all of you for the kind attention. Thank you. Thank you.
Thank you, Giovanni.
Yeah.
Very nice. We have time for a very quick question.
Thanks.
Either here or online.
Yeah. Maybe.
No, there are no questions in the chat. So
perfect.
No.
Yeah.
So this when the spin purification, you have these J-codes that you have to set.
Yes. Yeah.
Could you do it kind of adaptively? So
yes.
you know in advance what the spin value you want.
Yeah.
So you could have the program modify the J constant
until the. Yeah, I think. Yeah.
So it's not like an arbitrary parameter that we use. That's something that's
it can be adaptively adjusted. Yes, I think you're right. Yes.
You use ESD as starting point.
Excuse me?
What kind of starting point do you use? SD for the J coupling, or for the first initial guess for the J, or are you very or?
Okay. Oscar will, I think, will answer a little bit more into this. Yes.
Okay, so I think we have to move.
Thank you,
Giovanni, again.
There were questions.
Yes, maybe Giovanni, you can answer in the chat.
Oh, I will.
Okay. Yeah, because I think we have to move on.
But maybe you can answer why we prepare this.
Okay. So you could do, Stefan said you could do GASSCF also with the MRG. Technically, this is not an issue.
Oh, okay. That's not what Marcos Rai told me a few years back. But yes, if Stefan, I think I take it as true.
There's also a second question. Can you hear me?
Yeah.
Yeah. So regarding the latter, have you looked into what the Legesa does with this fermionic mode optimization in DMRG? Because that also compresses the wave function, and basically you get a very compressed wave function, and the orbitals essentially look at within the active space like very localized orbitals. So I guess that there might be a connection to that one.
You're right. I'm not saying that there is no compression in the MRG. I'm saying that the physics behind this compression is different. In fact, for instance, the best ordering, because you also rely on the ordering when you go into the final. Yeah. So the best ordering that you obtain for the MRG is not the same best ordering that we need to have into the many body wave function. So they are done by different physics. Okay, yeah. That I can understand, but just saying that also in DMRG there's something possible to optimize the content of the many body wave function in a DMRG representation. There might be a connection there as well. Yeah. Okay, I didn't find it, but yes, we can discuss. Excellent.
Okay, thank you. So, thank you.
Thanks.